all. Good evening, namaskar, sat sri akal, salam alaikum. I hope you're all well, fine, healthy. I welcome you all to this session, and it is going to be an amazing session, a very special session, and we have special someone uh, who is going to take us forward in this. So, guys, yes, you heard that right. You saw that right. This is a good and big chance to win 1 million US dollars via mathematics, and of course, it is not going to be easy. But yes. To take you forward and to tell you more about it, we have Aryan with us, who is also a student, and he's in class 8th, moving into class 9th currently. And he runs a Telegram channel. Uh, and yes, and very keen observant and amazing student. And of course, he's going to take us forward to how we can win $1 million via mathematics. So, Aryan, a bit about yourself before we start with the session.
Good evening, sir. Good evening, everyone. So, sir, as you already introduced, thank you for the introduction, sir. I am from class 8. So, I live in West Bengal and I live in a small city, Haldia. So I was just I'm keen in of the mathematics, and so I just came across this amazing 7 problems that if you solve, that you will get 1 million US dollars. So first of all, I was not believing this because I thought that mathematics is easy. But when I just saw the problems, I was like, what is this also possible? So today I will be taking you all through 2 of those 7 problems. Amazing. Because those 2 only I could understand as per my understanding goes. So, sir, can I share my screen?
Yeah, please.
So guys, I would first like to start this session by asking you some questions. How many of you are like crazy about winning $1 million, and how many of you are crazy about mathematics? I hope most of you, right? So let me get you through the 7 millennium problems, as the name suggests. It is the problem that if you solve one of these problems, you will get $1 million and a lot of fame in the mathematical society. So let us look at one of these problems one by one. But first, I would like to ask you that have you ever wondered that why are the prime numbers distributed in number line so randomly? Like 2, 3, 5, 7, 11, 13, then it again goes to 19, then 17, 23. And like this is like totally random. There is no specific pattern. Have you ever tried to, have you ever wondered why is it so? Also, have you ever tried playing with water? Like I am sure everyone did. And so I guess you believe that why does it behave like that? Also, if you have played with clay and molded it into like a shape of a house, a shape of anything, a pen, and so on, you would, I guess, you have did an experiment that you tried to fold a sphere in let's say, in a small sphere or a donut. Did you know that you can do this with any shape? You choose like a house, you can take the house, mold it, and it will form a sphere. But it took about a decade or maybe a century to prove this using mathematics. So let me give you some.
I mean, these are very obvious things, but again, when you're speaking about it, so it kind of hitting our mind. Yes, this is not very obvious, but yes. So I think we are in good for a good session and some interesting things to be explored.
Yes, sir. So like these problems are like so mind-boggling, so interesting that it will like force you to think out of the box to even understand what are these problems say. Right. So sir, the first problem is like the P versus NP problem, which we are going to see in today's session. This problem will give us an algorithm that is so strong that it can the problems which are taking the today's supercomputers for 300 quintillion years to solve, it can be just solved in 1 second if you get this, if you solve if you prove that P equals NP. Also, the Riemann hypothesis. Remember the prime number question I asked you? The Riemann hypothesis is entirely about the prime numbers. The next is the Young-Mills and the mass gap problem. This is also it. Now the complex realm starts. Here, this is a Young-Mills theory. If you have heard of this, this Young-Mills and mass gap problem is regarding if you have any solutions or are there any specific conditions where the solutions to Young-Mills theory exist? The next is the Navier-Stokes equation. It's like the F equals ma, force equals mass into acceleration. That's like the basic thing of classical physics. But this equation is the F equals ma of fluid mechanics, and it asks us that does this equation exist every time? The Poincare conjecture, if to be honest, is the only solved problem in this entire seventh list, and which was solved by Gregory Perelman in 2002. This problem is like the problem I asked you, that when you try molding a house into a sphere, can you prove that it will always work? This is the problem.
So this has been solved. So that means the person who solved it got $1 million already.
Yes, sir. So, but the very interesting thing in this is that he rejected the $1 million.
Oh, that is something that many of us would not do.
Yes, sir. But he was such a kind of person. He rejected the $1 million because he just solved this problem for his love of mathematics.
Great.
So, sir, like the next two problems are like the Kähler manifold. It's the Hodge conjecture is a problem in algebraic geometry. There is any concept called Kähler manifold that you will learn in higher sessions, and the problem is about is there any space of harmonic forms as equal to the space of cohomology classes, and this problem is a little tough to understand, so I would ask you to research more. And the last is the Birch and Swaneton diet, that it is a problem related to the behavior of elliptic curves. So let us get started in the real journey now from the to the Riemann hypothesis.
So basically, these are the 7 problems which are yet to be solved. In this, one of the problems has been solved, but the person who solved it did not claim the prize. And the rest 6 of the problems, which I understand, are yet to be solved. And if anyone solves any of these 6 problems, he is going to get $1 million.
Yes, sir.
And amazing. And this is there officially, right?
Yes, sir. This is official. This is done by the Clay. These problems are set by the Clay Institute of Mathematics in the year 2000.
Okay, great. So we will be discussing 2 of these 7 problems in great detail, right? So let us get started. Yes, Aryan.
So, sir, the first problem is the Riemann hypothesis, sir. So, sir, like Riemann hypothesis is a perfect example of that how beautiful math is. Sir, I remember from some of your sessions, you used to tell that we can use complex numbers and solve real life problems. Sir, I always used to wonder that how can we do that? This is the example that just startled me. This example showed me that complex number not only can solve real life problems, it can just enhance the way we live. So, sir, for a brief explanation of complex numbers, it is nothing. Just it is a number of the form a plus bi, where a is a real number, b is also a real number, while I is an imaginary number invented by humans, which is the square root of -1. And the complex number is written like a plus bi. So, for example, take the number 2 plus 4i, where 2 is a complex, 2 is a real number, 4 is also a real number, but I is an imaginary number. That makes this a complex number. Now, it is like a real number plus a real multiple of I. This is what you call a complex number, actually. So, sir, now if we move on, I hope we all have learned about a number line. So, the number line is specifically a line where you can plot any real number. For example, you want to plot the root 2. There is a method given in the R.D. Sharma of 9th where you can find how can you plot.
It is basically NCRT.
Yes, NCRT. And also, sir, you can also plot, for example, minus in the integers. You can also plot any rational numbers and so on in this line. But now let us make it a little more complex. Now what we will do, we will add the complex line in this real number plane. What is the complex line? The complex line is a line where all the complex numbers are there. All the imaginary multiples, means the real multiples of I are placed. For as you can see, sir, -1 into I, -2 into I, then 1 into I, then 2 into I, and so on. So now, now let me show you how can you plot in this. For example, take a value 1 plus I. So what you will do, you will just you can just go to 1 here, and here you will go to I, and you will find that this is a point where both of them meet.
Yes, and it is like coordinate geometry.
Yes,
Aryan's
sir.
plane, this is what we call it.
Yes, sir. So this is like quadrant geometry only, but a little bit advanced level.
Yes.
So this is a how to plot 1 plus I. Suppose you want to plot 2i plus 4, then you need to go look for 2i and 4 where did they intersect here. So plotting in a complex plane is really easy. Like if you plot the stuff in a coordinate geometry plane or the Cartesian plane, then you will understand how to plot it. So now let us see a very beautiful thing, sir. There are actually two types of series. One is called a convergent series, and the other is called a divergent series. So what is the convergent series actually? The convergent series, according to any mathematician, is that the series whose number of terms are infinite, but its
Converges
sum
to
is
point.
finite.
Yes.
Yes, sir. So, sir, I hope you have heard of the famous Ramanujan problem. That is like 1 plus 2 plus 3 plus so on is equal to minus 1 by 12.
Yes.
So that's an example of a convergent series. That's the example of a convergent series. It is infinite. Like it goes on till infinity. But it is stopping at a value that is minus 1 by 12. So but now there is many theories that the proof is wrong because it is not at all possible, and also there is some mistakes in the proof. But that's like a vague example. The Basel problem which I took, that's the sum of the reciprocal of the squares is pi square by 9, pi square by 6. That's the example of a convergent series. Also, there's a very interesting thing. Before going on to the interesting thing, I just learned to just give a brief idea about divergence series. It's like the sum who's infinite, like 1 plus 1 plus 1 plus 1 plus 1 and so on till infinity. It's infinite. It does not stop in a single place. Now what? Let us do one thing. Let us prove important thing. Let us prove that zeta of s for any value s greater than 1 is always converging. So if you see this proof, this is the now what is zeta of s? It's written as 1 plus 1 by 2 as the 1. Now let us do a thing. Let us just group them. Here you see that 1, then the second term has 2 terms, the third term has 4 terms, the fourth term will be having 8 terms, and so on. Now we find that this term is less than this term, where we are removing 1 by 3s and replacing it by 1 by 2s.
Yeah, so this is the kind of thing that we do a lot in JEE preparation, right? So,
Yes, sir. This is manipulation. We're manipulating
yes,
the
so a
series.
lot of class 11 and class 12 students are going to relate to this. Yes, so basically it is going to converge. So you're proving that zeta of s comes down to this and then you put some values of s, and
Yes,
you'll
it
prove
will
that it is
converge.
divergent. Yes.
Yes. So so there is a thing that for zeta equal 1, it will never converge. But for any zeta that is greater than 1, it will converge. Euler proved this, and it was not unknown to Bernard Riemann, who is the founder of this hypothesis. So now let us go to the next thing. As we now know that it is convergent for s greater than 1. Also this series, this function in Euler's time was not applicable in the negative realm. So if we take this, suppose this is the zero axis. Now this is the positive realm for us, and this is the negative realm. Now the function would only work in this positive realm during the time of Euler. So, but when Bernard Riemann came into the scenario, what he did, he used analytical continuation, as I told, and he just gave it to this negative realm also. He just pushed it towards the negative realm also, and hence what happened? We got the Riemann zeta function.
So negative means he put the values of x as negative.
Yes, sir.
The zeta
Like
function.
during the times of Euler, only integers values, positive integer values of s were allowed, x. But now, when during the time of during the time of Riemann, what he did, he just used analytical continuation, and he just proved that he can do this for any complex value also. Like at that time, he cannot just think of doing at integer level. Only you can do it positive integer, but he did for complex numbers also. So, like I have found many examples during my research that when you break the laws of mathematics, and then you will always are bound to find something new.
Great.
Yes, sir. So this is one of the conclusions I made. You break the laws of mathematics, you will find something new.
So,
Okay, sir. So
so you're saying mathematics laws are not to be taken seriously. Yeah?
yes, sir.
If you
But
want
if
to
you
score
want to make
marks,
a great
yes.
discovery,
If you want to do well in schools, maybe then yes. Otherwise, yes, you're right.
yes, sir. Like if in schools, if you break the laws of mathematics, like
-1.
you will be broken.
Yes.
So, sir, what happened is that he just he also proved that for any negative even number, a negative even integer value of s, it will always converge. Or no, and also he told it will not only converge, it will be zero. It's a zero. Like you are just taking some real. So when you are doing 1 by 2s plus and so on, as s is negative, this 2 will come in the numerator, and
Negative
hence
even.
you will get some of natural numbers, sir.
Negative even, you're saying, right?
Yes, sir, negative even.
Hmm.
So, for example, sir, let here s equal -2, let k is 1. So, what are the values? -2, -4, -6, and so on, right? So what will happen? 1 plus here, what is s -2? So minus will go to the numerator and turn positive, and 2 means 4, and so on. So it tells that the sum of the squares of integers is 0. So can you imagine that? So first of all, I want to ask you that.
No, it is very hard to imagine. Like, similarly, the Ramanujan's thing also, the sum of all, I mean, positive things becomes negative. That is hard to imagine. So again, I think that is in correlation with what you're telling.
Yes, sir. Like you like this stuff you cannot imagine only. Like when I was thinking that how can the sum of squares we all know turn 0?
Hmm.
But we have so these zeros actually are called trivial zeros, sir. So these trivial zeros we don't need them only, so we can ignore them. Like although they are like not at all trivial. So trivial is a term used by mathematicians to express things that they know, that they understand. Sir, I don't know how mathematicians understand how the sum of squares is 0. But anyways, we can call them trivial and we can just ignore them. But the main thing comes with a non-trivial zero. Sir, can you see a strip here? Wait, let me remove it. Remove the mark. Then I guess you will understand. Uh, so can you see a strip here?
Yes.
So this focus on the strips. This strip is the most important. So what happens is in this Riemann proof that all the positive zeros, means positive zeros, there can be more, but mainly, yes, so the non-trivial zeros that we are looking for are the zeros that mathematicians could not understand, but that's the name non-trivial. Are the zeros are all lie in this strip that Riemann proved. Okay, sir. Like this, take this strip, all the zeros for the zeta function. When you import a s, that makes the zeta function equal to 0. All the s lies in this strip. Now, sir. Now, what? Here comes the fun part. So, see a half line here that goes through this strip.
Yeah.
So this half line, and now Riemann further proved that every s, such as zeta of s is 0, lies in this strip.
Every value of s.
Yeah. No, Riemann did not prove. Riemann claimed that every value of s for which zeta of s is 0, and that is s is positive, like of course s is positive, all lie in this half strip. Now the problem comes here. Riemann told this, but he could not prove it.
Okay.
Mathematicians also checked for the first 10 trillion zeros, and still could not disprove the theorem.
Okay.
Now
So
the
basically, first trillion zeros for which zeta function is 0 just lies in this strip.
this strip only.
But there is no proof of this.
There is
Mathematically.
no proof of this. Now that's the problem only. The one who can prove this, that this lie, there lies a zero that is not in the strip, or all the zeros lies in this strip only, he will get $1 million.
Amazing. Amazing. So
Like you can
I'm
understand.
banking on you, Aryan. Maybe you can go ahead and prove or disprove this.
Thank you, sir. Also, sir, now I remember I told that this is related to prime numbers.
Yes.
So, sir, I will be showing you two things. How can I prove? Now, sir, you now this thing that is on your screen. So this means that this product of all the prime numbers, like 1 by 1 minus 1 by p to the power s, and so this product of all the prime numbers is equal to the zeta of s. So see this proof. So we know that pi square by 6 is 1 by 1 square plus 1 by 2 square and so on. And we will let us multiply both sides by half. You will find that when you're multiplying this by half, so you are finding some stuff cancels. And when you're multiplying and subtracting, some stuff cancel. Again, you're subtracting, some stuff cancel. Again, you're subtracting, some stuff cancel. And here, when you're canceling some stuff, this comes here because you're subtracting, and this is comes here. And observe the sieve of Eratosthenes here. You're cancelling all the multiples of 3. You're cancelling all the multiples of 5. You're cancelling all the multiples of 7, and so on. Or you're cancelling all the multiples of the prime number so that the next number you get is prime, and then you subtract it, and hence this thing comes. Now, and as it is useful, as it is valid for this, for zeta of s equal to, it will valid for zeta of s. That's proven, and hence what do we get? That that zeta of something is the product of the reciprocal of the one minus the reciprocal of the primes. So as you see this thing, that zeta of 2 is 1 by 1 minus 1 by 2 square into 1 minus 1 by 3 square and so on. So all the numbers, that 2, 3, all will be prime in this sequence. So this Euler proved this. Yes, just you can imagine how beautiful is this. Like you are taking the sum of 1 plus 1 by 2s and you're proving it to be, and you're proving a direct relation to primes where it does not have to do with anything. The prime does not have to do with anything.
Amazing.
Yes, sir. This is amazing, sir. I was telling that like this will blow up. This blew up my mind. Also, now this is a little complex part. We don't have to focus here. Just the thing is that when you take a zero, now let's get to a real thing. When you take a zero of the Riemann zeta function, you put it in this formula. This formula turns the zero into a wave. And when this formula turns the zero into a wave. So what we do? Let us see one thing. Now let us see this animation. Thanks to Hexagon videos. What we can do? First, we will take one. We will draw its wave here by the formula. Now we will we will add the wave. So adding a wave is simple. You just add the arrows. You will add the wave, and we will subtract the same wave from this. Now see, we will do the same for all the waves. Now you see that as there's only 3 zeros, but now let the number of zeros increase, as you can see here. If you see, it is like it's turning into a stair. Now, sir, this stair is bounce. That's a very important problem. It bounces off at prime numbers. So see the bounce at prime number. Now when the number of zeros turn infinity, you will get such a stair that,
which
yes, sir,
only prime numbers.
That only bounces at prime numbers, and hence we get our prime. We know how the primes are distributed.
So basically, if you're able to solve this, then
you know what is primes.
Yes. So basically, we'll be able to find the prime numbers, and it is easy to locate.
Know where they lie.
Prime numbers. Amazing.
Super. Yes, sir. Like this is like so this ends the Riemann hypothesis, sir.
Great. So this was Riemann, and I hope you've all understood what the actual problem is, right? So it is going to take a lot of time. It is not that easy as it sounds. $1 million, of course, is a lot of money, and of course, you will have to work hard to get this $1 million. But yes, so this is one of the unsolved problems of the modern times, and of course, it is going to get solved. Sooner or later, maybe one of you will be able to step up and solve this and get that prize money. Amazing, Aryan. So, can we move on to the other thing quickly?
Yes, sir. So now the next problem is very close to my heart. This is called the P versus the NP problem. And so this is a problem in computer science that is as hard as it is easy to explain. Sir, you will know what I mean by this.
Yes.
Yes, sir. Can you see this Rubik's cube in my hand?
Yes.
So, sir, like now this Rubik's cube is solved. You can tell it by seeing only.
Yes.
So, but now imagine I just scramble the Rubik's cube.
Okay.
So now, do you think that solving this Rubik's cube is as easy as checking the solution to this Rubik's cube that this Rubik's cube is solved?
I don't think it is that easy.
Yes, sir. Yes, sir. I even don't know how to solve the Rubik's cube, but I know that how what Rubik's cube is actually unsolved. So as you can see that this Rubik's cube is very easy to check that it is solved. But see this boy, he just his mind is blowing off when he's trying to solve the Rubik's cube. So, sir, the main thing of P versus NP problems are that are the problems that are easy to solve, are easy to check the solution to, also easy to solve. So, for example, take all the IOQM problems, sir. When I just see your solution of the IOQM problem, I am like, yeah, this is the answer. But when I actually sit to solve, I am like, no, I cannot do this.
Okay, I get it.
Yes, sir. So this is the thing. Like you cannot always tell that, but there is a very amazing thing that comes out of the problem of this. So, sir, this is the basic thing. You guys should know that k square. When you take for any natural number for k greater than 4, k square is always greater less than 2 to the power k. This you can prove by induction by the taking the base as k.
Yeah,
K
yeah.
equals 5, and you can so on. Yes, sir. So now we will be needing this result. So you just we can just remember this. But for now, let's see the next thing. So before that, sir, can we play a game?
Oh, sure.
Yes, sir. So what we have to do? There are two parts of this game. In the first part, what we will do is we will just take this 9 numbers. What you will do is that you will try to form 15 using this set of 9 numbers, and I will be also trying to form 15. But I will be also trying to stop you from forming 15, and who gets it first will be the winner.
So by 15, you mean some of the numbers in
Some
a
of the
row or
numbers.
column or diagonal is 15.
Yes, sir. So first, let's play in this table. In this not in the table, in this thing. Okay, sir. So let's do this. So who will go first, sir?
You go.
Okay, sir. I will choose.
Let me go.
I will choose 7, sir. Wait a second. What happened? Yeah. Yeah. So I will choose 7.
I'll choose 1.
1. Also, sir, I forgot to tell that the numbers must be 3. You cannot get to 15 before 3 numbers. The next number I will be choosing is 4.
4. I'll do 9.
9. Okay, sir. Abhay, sir, and sir, then I will be choosing. Okay, I already choose 4. Okay. So let me try by
I mean,
2.
it's very obvious choice. No, you can't choose 2.
Yes.
I already have 9 and 1, 10. And choosing 5 gives me 15.
So 5 you are choosing. Okay, sir. So yeah, like this only. You're saying that if I choose 15, then if I, for example, I lost the game. Like yeah.
But again, I get what you're hinting at. It is basically a tic-tac-toe. Right.
Yes.
So if you have this in your mind, then yeah, tic-tac-toe is what is I think NP version of this problem.
Tic-tac-toe is the polynomial version of this
Oh, it's
problem.
a
So this is the
polynomial
NP problem. NP version.
Yes.
It will take a lot of time to solve. For
Yes.
example, you can try, you can just for example, you're playing with someone else. You can try by trying to stop him, or you can guess. But in tic tac toe, the method that solves tic tac toe also will solve this problem. So this game is called number scrabble actually.
Hmm.
For example, here if I choose two, sir, can you choose a number?
Sorry,
Can you choose a number?
I'll choose 5.
Okay. Um. Okay, I will choose 4.
I'll choose 9.
Okay, so I will choose 1.
Yes, so I got it. So it is tic-tac-toe.
Yes, it's like tic tac toe only, but sir, it's like a different version. But it can be broken down into tic tac toe, right? Now this thing can be applied to many things, many problems. For example, there were some ancient problems that were thought to be NP complete problems. I mean, not NP complete problems. NP complete problems is not solved till now. NP problems. But once they changed the algorithm, the perspective as looking at the problems, they were able to solve it. So, for example, take the sorting example only. When you change the algorithm of the sorting example, you were able to solve it completely. You're getting so like you can just take a problem. You can just try to minimize the stuff. Sir, I also remember in one of your sessions you were taking you were taking two problems. The first problem consisted of a I guess the number was you had to take four numbers and you need to prove that I guess it was you use some zeros and the sum of the squares must be even numbers or something like that. I forgot actually. And next you took the IMO on the problem. In sir, it was in the representation the session of yours.
Okay.
Yes. Now the first problem you took, the second problem what you did, you took the IMO problem, you reduced the IMO problem to the same first problem, and we know how to solve the first problem.
Yes.
Yes, so that's only. But now the tricky part is that only we are not able to do in the NP complete problem because they're so complex.
Hmm.
Okay. So what we can do, we can just try to form an algorithm using that, and then if we form an algorithm for one NP complete problem only, all the other NP complete problems can be solved because all can be reduced to one problem only. This is the property of NP complete problems.
Great.
Okay, sir. So these are some of the NP complete problems which I told. So if anyone solves just one of these problems, he will be getting $1 million.
So I still have not got what NP problem means, and how are we going to solve it. But again, yes, I got the bigger picture that in general you have to reduce a problem to a level which is already solved, and to solve all the problems in less amount of time.
Yes, sir. Or else you can just bring out the algorithm. So, for example, when you solve some mathematical problems, the algorithms by which you solve those problems, I have never thought of it. Maybe there is some algorithms we're not thinking at that level that if we apply the algorithm, we will be able to solve NP complete problems. And sir, NP complete problems, I mean, why are they important? Because if you prove, now there is a thing, it is called P equals NP. So now what P equals NP really means is that when you are taking a polynomial problem, a problem that can be solved in polynomial time, and a problem that can be not solved in polynomial time, that means NP complete. You need to prove that is all the problems that are solved in polynomial time, means all the problems that are now not solved in polynomial time and takes a lot of time, can they be solved in polynomial time? You're getting it, sir?
Mm-hmm. No,
Yes,
not
sir.
exactly, but again, yes, a little bit it is making sense.
Yes, sir. Like this was a little difficult for me to grasp as well, and I have to be honest. I still am not able to grasp this problem, or I am still not be able to just think on what lines should I think to
Yeah,
solve
but
this.
I guess yes. So, what you have really told is about the seven problems and discussed the two of them. Of course, you've given the summary of these problems and what they are,
Yes,
and
sir.
the detailed version. Of course, they can all be googled, and the audience can always Google these seven problems. And again, it is going to require a lot of mathematics. It is going to require a lot of depth in
Yes,
terms of mathematics to solve this. But yes. Yeah.
So the first lesson which I've taken is that mathematics is really beautiful, both visually and practically, and it's the art of connecting and knowing about two different things of the world. So like biology and maths are like completely different, but you can connect them.
Great. I mean, this is going to be a good news for a lot of students who don't like, biology.
Yes, sir. And the second thing is, of course, there are easier ways to earn $1 million, guys.
Yes, right, Aryan. So thank you, Aryan, for this amazing input and amazing depth into these problems. Of course, these are very difficult problems. They have not been solved by human beings as of now, and of course, it is. I mean, it is a matter of time before they get solved, and whoever solves this is going to get 1 million USD, and which is a good, amazing amount of crazy amount of money. And yes, it is going to take a lot of efforts. So all the best, guys, and. What I can say, I mean, do your best, make us proud. Thank you, Aryan, for this. And all right, guys, take care. See
Thank
you.
you.
God bless you. Bye, all.